So let us resume where we have left. So we were at the question number 26. Describe the limitations of the pumping lemma for proving non-regular languages. So the pumping lemma is a useful tool for proving that certain languages are not regular, but it has important limitations. It is only a necessary condition for regularity, not a sufficient one. This means some non-regular languages may still satisfy the lemma, and the lemma cannot prove that a language is regular. These are the key limitations of the pumping lemma. First is it is only a necessary condition. That is, all regular languages must satisfy the pumping lemma. However, not all non-regular languages fail it. Some non-regular languages can still meet the lemma's conditions. So the lemma cannot detect all non-regular languages. Second limitation is it cannot prove regularity. If a language satisfies the pumping lemma, it does not guarantee that the language is regular. Example is certain non-regular languages may accidentally satisfy the lemma pumping property, so the lemma cannot be used to prove regularity. Third limitation is dependency on string choice. The proof technique requires choosing a string of length greater than equal to n, that is the pumping length. If the chosen string is not appropriate, the argument may fail even though the language is non-regular. This makes the lemma tricky to apply in practice. Fourth limitation is the limited scope. The lemma applies only to regular languages. For other language classes like context-free languages, you will read these context-free languages later on as a part of the syllabus of ED. So for other language classes like context-free languages, a different version of the pumping lemma exists, but it has similar limitations. Constructive proof are hard. The lemma is often used in contradiction proofs, assuming regularity, then showing pumping fails, but it does not provide a constructive method to build automata or grammars, limiting its practical use. Example of limitation can be seen using this example. So consider this language a raised to power p, where p is prime, that this language is non-regular. However, proving it with pumping lemma is extremely difficult because pumping may still produce strings that look valid for certain primes. Instead, more advanced techniques like the Mihill-Nerod theorem are needed. So this is the summary. You can read it at your own. I have told you the limitations of the pumping lemma. Now we jump to question number 27. Use the pumping lemma to show that language L equal to a raised to power n, b raised to power n, where value of n is greater than equal to 0 is not regular. So recall the pumping lemma. If L is regular, language L is regular, then there exists a pumping length P such that any string W belong to L with the length of that string W should be greater than equal to P can be split into three parts. That is, the string W can be written in three parts X, Y, Z, satisfying these three conditions. That is, the length of the XY should be less than equal to P, length of Y should be greater than 0, and for all values of I greater than equal to 0, X, Y raised to power I, Z belong to the language L. Now, step 2. Choose a string in language L. Let us pick this an example string W is equal to A raised to power P and B raised to power P. This string is clearly language L because this string contains equal number of A's followed by B's, right? So A raised to power n, B raised to power n, equal number of A's followed by B's. Now we have to apply the lemma's condition. Since the length of the XY should be less than equal to P, both X and Y consist only of A's because the first P characters are all A's. As you can see, the first P characters are all A's because A raised to power P is there. So that's why we have to split in these parts. X will be A raised to power K. Y should be, because XY should be power of A. So that's why Y should be equal to A raised to power M. So with M greater than 0, and Z will be the remaining power of A, that is P minus K minus M, right? And B raised to, followed by B raised to power P, right? Following the pumping lemma. Step number 4 says that pump the string. Now consider pumping with I is equal to 0. In this case, we substitute value of this. See this X, Y raised to power I, Z. This condition X, Y raised to power Z belong to L. So take value of I as 0. Take value of I as 0. So X, Y raised to power 0 Z. Because Y raised to power 0 means no, Y raised to power 0 means nothing. So we are left with XZ. X is what? X is A raised to power k, and z is a raised to power p minus k minus m. So it will become a raised to power p minus m followed by b raised to power p, right? So this string has fewer a's. You can see clearly here. You can see this string. This string. This string has fewer a's than b's because number of b's are p. Number of a's are less than p's. So now this string has fewer a's than b's. Specifically, there are p minus m a's and there are p b's. Clear? But in the problem, what has been given to us? A raised to power n, b raised to power n. That is, number of a's should be number of b, right? The number of a should be equal to number of b. So that's why there is a contradiction. But L is equal to a raised to power n, b raised to power n requires the number of a's and b's to be equal. So there is a contradiction. That's why x y raised to power x y raised to power 0 z does not belong to L, which was the condition of the pumping lemma. Which was the condition of the, this is the condition of the pumping lemma. X y raised to power I z should belong to L. So this is, there is a contradiction now. X y raised to power 0 z does not belong to L. So there is a contradiction. This contradicts the pumping lemma condition. That is x raised to power y z belong to L. This condition is violated. So we reach to conclusion. So therefore our assumption that L is regular. We have earlier assumed that L is regular. So this is false. That's why L a raised to power n, b raised to power n is not regular. But what we have to show that it is not regular. This contradicts the pumping lemma condition. So our assumption that L is regular, what we have assumed. So we have already assumed if L is regular, okay, if L is regular. So our assumption was L is regular, but this is a contradiction. So that's why this we have proved that L is equal to A using the pumping lemma. We have proved that language L equal to A raised to power B raised to power n is not regular, right? Because we have already assumed L is regular, but it violates pumping lemma. That's why L is not regular. Now we jump to question number 28. Convert the following NDFA to equivalent DFA. We have already done it. I will not be solving or showing you the explaining the steps again because we have done already this type of problem, conversion of NDFA to DFA. However, I can show you the desired DFA. You can draw at your own, right? This is the desired DFA. Okay, right? Now, question number 29. Question number 29 says that explain the difference between Mealy and Murray machine. We have already done. These are the finite state machine, already done. Question number 30. Design a regular expression for the set of strings over 0, 1 that do not contain 1, 1. So we have to design a regular expression that do not contain 1, 1. 1 should not be followed by another 1. So we have to design that regular expression. Input symbols are 0, 1. So see question number, answer to question number 30. So see here, this is the desired regular expression. This is the desired regular expression. All this. This is the answer. That is, pipe symbol means what? 0 or 1, 0. Then asterisk means 0 or 1, 0 can occur how many number of times? 0 or more than 0 number of times. Already explained to you. Star means 0 or more than 0 number of times. Plus means 1 or more than 1 number of times. Clear? So either 0 can occur 0 number of time or more than 0 number of time. And this string 1, 0, that is 1, 0 can occur 0 number of time or 1 number of time or 2 number of time or 3 number of time. That is, you can write empty, then 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, so on and so forth. And after that, one question mark. So this is the regular expression for the problem. So whenever you will be drawing the transition diagram using this regular expression, this is the transition diagram on the right hand side. When you reach the final state, you will never see 1 followed by 1, which has been asked to do so. that do not contain 1 1. Clear? So this is the desired answer to our problem. Now see question number 31. Explain the difference between union and concatenation operations on regular languages. So union of regular languages. Definition: if L1 and L2 are two regular languages, their union is given by L1 union L2, that is equal to W, such that W belong to language L1 or W belong to L2. The union contains all the strings that belong to either L1 or L2, right? Union is like logical OR, you already know. Example: L1 equal to A raised to power n, where n is greater than or equal to 0, that is all strings of only A's. L2 equal to B raised to power n, all string of only B's. So L1 union L2 will be A raised to power n union A raised to power, sorry, A raised to power n union B raised to power n, right? So that is all string consisting of only A's or B's. Union means or. So all strings consisting of only A's or B's. Both can also occur, but A's or B's. You already know what is union. Similarly, the concatenation operation, concatenation of regular languages. If L1 and L2 are regular languages, their concatenation is given by L1 dot L2, that is XY. You take the combination, concatenation of both of them, where X belong to language L1, Y belong to L2. So concatenation means joining one string from L1 with one string from L2. Concatenation is like sequence. For example, L1 is A raised to power n, L2 is B raised to power n. So concatenation of L1 and L2 will be A raised to power n, B raised to power m. That is value where value of n and m is greater than or equal to 0. So number of A's and number of B's can be different, but you can combine both of them, concatenate. So that is all string of A's followed by B's. However, the number of A's can be different from number of B's, but it will contain all the strings consisting of A's followed by B's, some number of B's. So this is the definition of union and concatenation in the form of a table. So this was the answer to question number 31. 31, that is union and concatenation on regular languages. This is the summary. You can read it at your own. Now we jump to question number 32. Construct a DFA for the language. So this is the regular expression given to us. You can easily draw DFA or transition diagram. You have to draw basically. You can also draw the transition table, but from this regular expression given to us, you have to draw the transition diagram for the corresponding deterministic finite automata, right? So first of all, you have to focus on the given regular expression. Answer to question number 32. Yes. What is the regular expression? A plus B. A plus B means A or B, right? Star means 0 or more than 0 occurrences of A or B, right? Followed by A, B, B, right? So if you see, this is the required answer. This is the required DFA transition diagram. You can also draw the transition table by referring to this transition diagram also. So if the question, it depends on the number of marks of question which has been asked in your exam. If the question is of more marks, then you have to draw both transition diagram and transition table. Otherwise, you can draw at least one of them. So as you can see here, Q0 is the starting state because it has been marked with Q0. So then we apply A on Q0, next state is we got is Q1. Then we apply B on Q1, next state is Q2. Clear? And here the missing is some input symbol is missing here. So for drawing this complete transition diagram, you can refer to this transition table, right? So this is the desired solution to our problem. When you see this transition diagram, you will see that Q3 is the final state here, and you will see it will obey this regular expression. That is, when you start with the initial state Q0, then A or B, as you can see A, right? Then A, then here it should be B because ending with A, B, B. So it will be B here. It will be B here. Let me correct it. It will be B here. It will be B. So it clearly it is ending with A, B, B. So Number of questions we have solved so far. Number of questions we have solved so far. So you now you are in a position to draw. You can draw any transition diagram by referring to a given regular expression. Now we jump to question number. We jump to question number 20. Sorry, 33. 33. So 33 prove that every DFA can be converted into an equivalent regular expression using Arden's theorem. So Arden's theorem says that every DFA can be converted into equivalent regular expression. In 32, we have done the vice versa. We have drawn the DFA from regular expression. Arden theorem, with that Arden theorem, we can convert DFA to regular expression, vice versa. So see, what does the Arden theorem say? Arden theorem says that if we have a language equation of the form R is equal to Q plus RP, where R, QP are regular expressions, then the unique solution for this equation is given by R equal to QP star. Star means 0 or more than 0 occurrences of P. This theorem is fundamental in converting DFA or NFA into regular expressions, right? So how to convert a DFA into regular expression? These are the steps of the Arden theorem. Suppose we have a DFA with these set of states Q1, Q2 up to Qn. For each state Qi, we write an equation such that regular expression Ri input symbol leading to another state. So sigma, first sigma is contain the input symbols leading to another state plus this sigma indicates input symbol leading to back to itself. So Ri will represent the set of strings that take the automata from start state to state Qi, right? Starting, that is initial state to state Qi. The step number of 2 is to apply the Arden theorem. That is, each equation is of the form Ri equal to Qi plus Ri into Pi. By Arden theorem, Ri equal to Qi into Pi star. That is, star means 0 or more than 0 occurrences of Pi. Thus, we can eliminate recursion and express Ri as the regular expression. Now, see this example. Suppose consider a DFA with two states, Q0 as the starting or initial state, Q1 as the final state, and these are the transitions given to us, right? So based on these transitions, you can draw the transition table for yourself, right? So if we apply an input symbol A on Q0, we get the next state Q0 itself. When we apply input symbol B on Q0, we get the next state as Q1. When we apply input symbol A on Q1, we get the same state Q1 as the next state. So for Q0, the equation will become R0 equal to what was the equation? Ri equal to Qi plus Ri into Pi. So it will become, sorry. So how will you write it? R0 for Q0. For Q0. So when we apply input symbol A on Q0, what we are getting? Same Q0. That's why AR0. When we are applying B on Q0, we are getting next state Q1. So that's why BR1 plus epsilon, because epsilon means empty. For Q1, we apply same. For when we applying A on Q1, what we are getting? Same state Q1. That's why we're getting R1 equal to AR1. So I hope you have understood how to write these two equations. We have written these two equations for Q0 and Q1, for Q0 and Q1 by referring to these transitions. Please focus. Right? Now we'll be applying the Arden theorem to convert this DFA into regular expression. Right? So now for R1, this R1 equal to epsilon A star, right? Why? Because R1 equal to AR1. So as soon as you are trying to apply A any number of time, you will get R1. If you focus on this, R1 equal to AR1. So R1, regular expression R1 will be given by epsilon A star. For R0, what it is? R0 equal to AR0. So epsilon we will be writing. Epsilon is the empty. So AR0. So AR0 plus BR1. And what is R1? R1 is A star. So substitute value of R1 here. So it will become what? R0 will become epsilon plus we take epsilon plus In place of R1, we will substitute A star, right? And in place of R0, just a minute, epsilon plus, okay, this will become this right part. R1 is A star, so it will become B A star. So epsilon plus B A star. And what is AR0? So AR0, it means we are getting, we are trying to apply R0 equal to, R0 is AR0. So we are trying to apply A and A any number of times, zero or more than zero number of times. So that's why we have written here, it is written as A star, right? Let me repeat it again. Just a minute. How we have got this? See, how we have got this? For R1, this has been obtained from this, right? So we are trying to apply A any number of times. So obviously we are getting R1 equal to A star, right? And R0 will be equal, is given by epsilon plus A0 plus BR1. We have already given this formula. Now, in place of this R1, we substitute A star because epsilon is nothing, empty. It is empty. So in place of R1 here, we will substitute A star. So this will become BA star. So this will become epsilon plus BA star. And now, uh, because R0 equal to AR0, again it will become A star. So this will become A star. So we have got, finally we have got this final regular expression. So regular expression, what is given by this A star. This A star comes first, right? Then followed by B A star. So in this manner, we can convert a given DFA into regular expression using the Arden theorem. Now, if the similar like type of problems occur in future, you have to solve yourself. However, I will show you the solution only. The detailed steps have already been explained to you. Clear? How to convert a given DFA to regular expression using Arden theorem. This is the conclusion. You can read it at your own. Now we go to question number 34. We go to question number 34. Convert the following NDFA to NDFA. So such type of problems we have covered previously also. I will not be repeating again the detailed steps, but however, I can show you the solution only. So this is the desired result. Desired DFA. This is the desired DFA, required DFA. Now you know how to convert a given NDFA to DFA, right? So this is the answer. Now we move to question number 35. Explain the subset construction method used to convert NFA to DFA. So far as whatever method we have used to convert NFA to DFA, that is known as subset construction method, right? The method of converting NDFA to DFA, the same method is, the name of the method is subset construction method. So we have already dealt with it. I will not be explaining again because 34 and 35 are the same. Question number 34 and 35 are the same question, similar type of questions. Now we go to question number 36. We have to design a DFA that accept all the strings over A and B, where A is immediately followed by B. 36. So A is followed by, it is saying A is immediately followed by B. So as you can see, when we start from Q0, here Q0 is the starting state as well as initial state as well as final state. Because arrow indicates it is a starting or initial state, and double circle means that it is a final state also. Double circle means that it is also a final state. So what has been given? We have to derive a DFA where A is immediately followed by B. So when we start A, so A is now followed by B. We are getting to the same final state, and A is followed by B. And this loop means you can apply B number of n times. So we are getting A immediately followed by B. And these are the remaining possibilities only. Right? These are the right hand side in the transition diagram. These are the remaining possibilities only, but we have to notice the major portion. A is immediately followed by B. So this is the DFA for the given problem. Now we are enough expertise to solve the, you are having enough expertise to solve the required problems. Now question number 37. Explain the process of converting a regular expression to NFA using Thompson construction method. 37. So I will tell you how to convert a regular expression to NFA, non-deterministic finite automata. Regular expression is given to us. We have to convert that regular expression to NDFA using the Thompson construction method. So let me explain to you this method, and you can refer to this method to convert the regular expression into NFA. So Thompson construction method is used to turn a regular expression into NDFA or NFA. Think of it like building with Legos. Every part of a regular expression has a specific building block or template. To create the final machine, you simply snap these blocks together using the glue is called the epsilon transitions. I have already told you how to remove the epsilon moves from the epsilon NFA, which are the paths the machine can take without consuming any input. I have already shown you. Here are the basic rules how to convert a regular expression to a NFA by the Thompson construction method. Every machine built with Thompson method has exactly one start state and only one final state. Thompson construction method says that every machine built with Thompson construction method has exactly one start state and only one final state. For a single character A or input symbol A, draw two states with an arrow labeled A between them. Okay, this is the step. Draw two states with an arrow labeled A between them. For an empty string, draw two states with an arrow labeled epsilon, right? So there are three main rules of Thompson construction method that are also known as connectors. First is concatenation, that is A concatenated with B. This means A followed by B, you know. To connect them, you take the final state of machine A and connect it to the start state of machine B using an epsilon transition. That is, logic behind is you must finish A before you can start B. B part is union or selection, that is A or B. This means either A or B. You create a new start state and a new final state. From the new start, you draw two epsilon arrows, one to start of A and one to the start of B. From the ends of A and B, you draw epsilon arrows to the new final state. So logic is this creates a fork in the road where you can choose which path to take. C step is clean star. So A star is known as clean star. So this is known as clean star operation. Zero or more than zero occurrences is known as a clean star operation. This means zero or more of A, that I have already told you. That is zero or more than zero occurrences of A. So you take machine A and add a loop back and shortcut. Create a new start and new final state. Right? This is the first step. Create a new start and new final state. Add an epsilon from the new start state to the new final state. This is a zero times path. It skips A entirely because epsilon means empty. Add an epsilon arrow from the end of A back to the start of A. Right? Add epsilon arrow to connect the add epsilon arrows to connect the new states into the flow. Step-by-step example. For example, we have been given this expression, that is A or B star, that is zero or more than zero occurrences of A or B. So now you have to convert this regular expression into NFA using the Thompson construction method. So now now listen carefully. How to convert this regular expression into NFA using the Thompson construction method. So to build NFA for this regular expression, we have to follow this order of operations. First step is says that build A and B. That is, create two basic blocks for the character A and B, right? Then you have to apply the union. This is the next step. That is A or B. So use the fork in the row template. Now you have a machine that can pick A or B, right? Apply the clean star operation. That is, wrap the entire fork machine in the clean star template. Add a shortcut to skip it. That is zero repetitions because empty is. Add a loop back to repeat the choice of A or B as many times as you want. So if the Thompson construction method is still not clear to you, if some example is coming in the later questions, I will explain with the help of an example, real life example. I will be explaining later on the Thompson construction method, how to convert a given regular expression to NFA. Later on, please have patience. Now the next question is question number 38. Define a language that is regular. Define a language that is regular and provides its corresponding DFA, NFA, and regular expression form. Right. So question number 38. So define the language. Let us take a simple regular language. L equal to W belong to A comma B star, that is 0 or more than 0 occurrences of A and B, A or B. W ends with AB, that is the string should end with AB. This language consists of all string over alphabet A and B, that is A and B are input symbols, and it end with the substring AB, that is all strings that end with substring AB. So what is the regular expression for this? You have to only focus on the string should end with AB. So this is the desired regular expression for the given which example we have taken, which language we have taken, regular language. So first of all, what the question has been asked in question, that is define a language that is regular and provide its regular expression form. So this is the desired regular expression for this language, right? Second, so A or B star means A or B can occur 0 or more than 0 number of time, but the desired condition should be fulfilled. That is, it should be end with AB. It should end with AB. So this we have solved. We have obtained the regular expression, right? Also, we have to design DFA and NFA. So for deriving the DFA, how to obtain the DFA? These are the transitions you can. Earlier, I have shown you several problems where, based on regular expressions, you can obtain the desired DFA. So you can obtain the desired DFA. These are the transition stones. You can draw the transition diagram at your own by referring to these transitions, right? And once you are having a DFA, then you can draw the NFA, because I have already told you the subset construction method to convert. Sorry. Thomson construction method is still remaining. How to convert a regular expression to NFA. Thomson construction method is still to be seen by us, because we have not seen the sole example of Thomson construction method. For which purpose the Thomson construction method is used? For converting the regular expression to NFA. So regular expression we have already obtained using the Thomson construction method. You can convert this regular expression into NFA. So I will be showing you the Thomson construction method with the help of an example later on, right? Now we jump to question number 39. Explain why all finite languages are regular with a proof. So a finite language is a language that contains only a finite number of strings. A regular language is one that can be described by a regular expression or recognized by finite automata, DFA or NFA. So what it is saying, why all the finite languages are regular? Why all finite languages are regular? We have to prove. So step number 1, any single string is a regular for a single string W which belong to epsilon star. We can construct a regular expression that matches exactly W. That is, suppose the string W is given by ABA, corresponding regular expression is there ABA. So that, and DFA is a chain of state consuming A and then B, then ending in a final state. Thus every single string is regular. That's why all finite languages are regular. Step 2, finite union of regular languages is also regular. Suppose L1 and L2 are regular, so union of them is also regular. So we can construct the finite language in step number 3. Suppose language L consists of these strings W1, W2 up to Wn. Wi is regular. So L can be written in the form of union of W1, W2, W3, and so on, so on. So union of regular languages is regular. So L is regular. So that's why these are the steps. This is the given proof why the all finite languages are regular, right? Question number 40. Convert the following NDFA to DFA. Again, we have solved earlier using the subset construction method. So I can show you the solution only, but I will not be explaining the steps. So this is the solution to problem number 40. Clear? This is the solution to problem number 40. I can show you the resultant DFA. So this is the final transition diagram for the resultant DFA, and based on this transition table, you can draw the desired transition diagram for DFA, right? This is the desired equivalent DFA, right? Okay. So question number 40 is same. Now we jump to 14 for statement number, question number 41. Write the statement of Arden theorem. Please give me 1 minute. I have to attend a call. Then we will be resuming with question number 41, right? So question number 41 says that write the statement of Arden's theorem. We have already seen Arden's theorem. For your convenience, let me show you the Arden theorem again. So this is the same Arden theorem which we have discussed already. If you remembered, we have already seen this Arden theorem in action with the help of an example also. Clear? So this is the Arden theorem. So now we move to question number 42. In question number 42, we have to design a regular expression for the entire set of strings for input alphabet 0, 1. So 0, 1 are input symbols containing at least 3 ones. So this is the desired regular expression where you can see we'll be having when we derive a string using this regular expression, then we will see the resultant string will be having at least 3 ones. Resultant string will be having 3 ones. For example, if we take 0 plus 1, 0 plus 1 means 0 or 1, star means 0 or more than 0 occurrences of 0 or 1, then there is 1. There will be definitely this one, then there will be definitely this one, then there will be definitely this one. So there will be at least 3 1 in this in the string obtained using this regular expression. So the desired regular expression is given by this. I hope you have now clearly understood the problem, and now you are in a position to draw the regular expression for any given problem statement, right? So this is the solution to the problem. Explanation is given to you, which I have earlier explained to you. That is 0 plus 1 star means any string of 0 or 1, 0 or 1 occur, but these ones, 3 ones will occur definitely. These 3 ones will occur definitely. So there will be at least 3 ones, right? Clear? Now this is the explanation you can read, and these are the accepted strings. In the first example, you can see there are at least 3 ones. In this also there are 3 ones. In this 3 ones. In this case also 4 ones. At least 3 ones are also there. And the non-accepted epsilon means there is not a single one. We require at least 3 ones. These are not accepted. 0 in 0 we are not having 3 ones. 1 0 1 0 in 1 0 1 0 we are having only 2 ones. We require at least 3 ones. So these are the strings which are not accepted. Now we jump to question number 43. State and prove Arden theorem. State and prove Arden. Arden theorem, I have already told you this is the Arden theorem. Now we have to prove this Arden theorem. So see how to prove this Arden theorem. Step 1 is substitution. We start with the equation R is equal to Q plus RP. So this is the Arden theorem. What is the Arden theorem? Arden theorem states that let P and Q be regular expressions over alphabet sigma. Consider this equation R equal to Q plus RP. So this is the statement of the Arden theorem. Now substitute R in place of on the right side. In place of R, keep on substituting Q plus RP because value of R is Q plus RP. So substitute Q plus RP again and again on the right side of this equation in place of R. right? Continuing this expression, what will be getting? Q plus QP plus what? RPP. And continue this expression, R will be equal to R equal to Q plus QP. Then just a minute. When you are substituting Q plus RP in place of R, so it will become Q plus QP plus RPP. Okay. Now again, yes. Now again, in place of this R, you will substitute Q plus RP. So you will get, finally you will get this expression, R is equal to Q plus QP plus QP square plus QP cube plus and so on and so forth. Step 2 is factorization. Step 1 was substitution. Step 2 is factorization. What is factorization? Take Q common. So after taking Q common from right hand side, it will become R is equal to Q common. Within the parenthesis, it will become 1 plus P square plus P3. By the definition of clean star, what is this? 1 plus P square plus P3. This is nothing but P star. That is 0 or more than 0 occurrences of P. 1 means 0 occurrences of P. P means 1 occurrence of P. P square means 2 occurrences of P. P cube means 3 occurrences of P. Understood? So it will become, now this expression will become R equal to Q, and this is what? P star. So what we will get? R is equal to QP star. So hence proved. This is the Arden theorem. R is equal to QP star. R is equal to QP star is the Arden theorem. This is given equation, and this is the, we have proved, this is the Arden theorem, right? So we have successfully proved the Arden's theorem. Now we jump to next question. That is question number 44. Design a regular expression for the entire set of strings or the input alphabet 0 and 1 are input symbols containing exactly 3 ones. So there should be only 3 ones. So this is the regular expression. So now you are in a position. So you can see here 0 star means the 0 or more than 0 occurrences of 0, right? And you can see if you derive some string from this regular expression, there will be exactly 3 ones. One, this one, second one, this one, and third one. There will be exactly 3 ones only. See here, clear? So we have derived the regular expression for the question number 44. That is, we need exactly 3 ones, right? So this is the explanation. You can read it at your home. I have explained already. You can read it at your own how to derive a regular expression that contains only exactly 3 ones. Now we jump to question number 45. So these are some of the accepted things. We can see there are exactly 3 ones in each of the cases. In not accepted strings are 1 1. There are only 2 ones. Here are only 4 ones. We need exactly 3 ones. So these are the not accepted strings. Now we jump to 45. Question number 45. Write the statement of pumping lemma for regular language. So we have already solved a example to prove the pumping lemma theorem. So already done. So I can show you the solution only. We have already discussed the pumping lemma theorem. Furthermore, we have proved that using the pumping lemma that L is not regular. We have already proved. So this is the pumping lemma which we have already discussed in the previous few problems or questions, right? Now we jump to question number 46. Question number 46 says that design a regular expression for the entire set of strings over input alphabet sigma 0 1 containing at most 3 ones. So there should at most 3 ones. That is, there cannot be 4 number of ones. There cannot be 5 number of ones. At most 3 ones should be there. There can be 2 ones. There can be 1 1 also. There can be none of the 1 also. But cannot more than 3 ones. At most only 3 ones. So the desired answer is this regular expression. When you derive some string using this regular expression, you will find that there will be at most 3 ones. You can see here this one, then 2, right? Then okay, because this plus sign means either this or this. So in this case only one will be there. Plus means or, So in this case, only 2, 1 will be there. Okay. Plus means or. In this case, only 3, 1 will. So either number of 1 can be 0, number of 1 can be 1, number of 1 can be 2, number of 1 can be 3, but not more than 3. So number of ones can be at most 3. So this is the desired regular expression. This is the explanation which I have already explained to you. Clear? So this is the desired regular expression and henceforth the answer to the given problem. Now we solve the question number 47.